In this video, we're going to take a look at the arithmetic of equations, understanding how chemical quantities within a chemical reaction all relate to each other. Looking at a chemical reaction, it works the same way that a recipe does when baking. You can take all the amounts of reactants that are going in and relate them to all the amounts of products that are coming out, just like the ingredients that are going in for what you're going to be baking. I then can use those proportions and keep them relative to each other to then get a desirable outcome. If I'm having a large group of people over and my recipe calls for only 12 cookies that are going to be made from a certain recipe, and I have 20 people coming over, well, I'm probably going to need to double, triple, maybe even quadruple that recipe to make sure I have enough cookies for my company. And just like in baking, when I'm trying to make my 4 times the recipe and I figure out how much of each ingredient I need, I do check to make sure I have enough of those ingredients before I start, because I'm going to be calling my neighbor up to try and borrow an egg. Chemists will do the same thing. If they have a certain amount of product that they need to obtain to meet a certain manufacturer's desire, then they need to make sure they have enough of that reactant to then start off that reaction. So chemists can use this balanced chemical equation to, again, determine how much reactant or how much product will be formed looking at those relative amounts. I can relate any reactant to another reactant, a reactant to a product to a reactant, or a product to another product, looking at those ratios that are there between them and how they relate to each other on either a micro or macroscopic level. And that is called stoichiometry, when you're doing calculations of chemical quantities looking at a chemical reaction. So not just taking grams of one substance and putting it into moles, or liters of a substance and putting it into moles, actually looking at how 2 different substances within a certain chemical reaction relate. And 2 different substances may relate one way in a chemical reaction and then have a different proportion in which they relate in another chemical reaction. Let's take a look at this with something that might be a little more familiar to us before we get into a chemical problem. Here we have teeny toddler tricycles, and when teeny toddler tricycles is looking to manufacture their tricycles throughout a work week, they're going to get a delivery on Monday morning. And all the parts they need for the entire work week are going to be delivered that Monday morning. Well, if the manufacturers at teeny toddler tricycles can make 250 tricycles in 1 week, how many pedals need to be delivered there for Monday morning? So let's take a look at what a tricycle is and how it all relates and how we can put all this together. So here's a tricycle. I'm looking at this tricycle. I know it's made up of a frame. It's got 3 wheels, a seat, 2 pedals, and handlebars. And when I put all of those together, kind of like a synthesis reaction, I get back out one tricycle, this FW3SP2H. Again, that frame, 3 wheels, seat, 2 pedals, and handlebars all coming together, combining to make my one singular product. So then we're going to analyze and figure out what do we know, what do we not know. Well, I know that I need to make 250 tricycles in this work week, and I don't know how many pedals I need to be delivered there. So how can I relate tricycles to pedals from my balanced chemical equation? I know for every tricycle that is made, I need 2 pedals to make it up. I can relate, again, frames or seats or wheels or handlebars all to the tricycle, but in this case I'm just looking at how do pedals relate to my tricycles, because that's what the question's asking. So I'll take my given, put it over 1, take that 250 tricycles which are going to make throughout the week, put it over 1. Now I need to reduce out tricycles and get 2 pedals, and I can use that relationship of 1 tricycle needs 2 pedals. Again, a conversion factor because they're equal to each other. I'm not going to change the overall value, but tricycles divided by tricycles reduces out, leaving me with pedals, which I'm trying to find, and I see that on Monday morning I need to make sure there are 500 pedals delivered to my factory in order to make our 250 tricycles for the week. So within a chemical equation, we can look at it, again, both microscopically and macroscopically. I can look at the different quantities of whether it be atoms, molecules, moles, mass, or volume, depending on what the substances are that are involved. So atoms, as we know, when we balance equations, that the number of atoms of each element that go in have to equal the same amount of atoms of each element that are produced. So those are always going to be balanced, and I can look at the subscripts and coefficients of that balanced chemical equation to determine how many atoms there are of each substance. And again, they do need to balance out. I also look in terms of molecules. Using the coefficients, if I have molecular compounds, I then can relate different molecules of different substances to each other, both in reactants and in products, and determine how many molecules of each substance is going in and how many molecules of each substance is coming out. I then can use those coefficients and look at it on a macroscopic scale and call them moles. So if I have those number of molecules or atoms that are involved, if I take 6.02 times 10 to the 23rd of them, well, now I'm looking at moles. And again, as I already discussed, if you double, triple, quadruple, then keep those proportions the same, then the overall relative amounts of everything works out and is okay. So the same thing works out here. Rather than pick double, triple, or quadruple, I'm going to use 6.02 times 10 to the 23rd, use Avogadro's number. But if I multiply every single one of my reactants and products by that amount, then it works out all right. So I can use those coefficients as moles and look at it in terms of moles of reactants versus moles of products. Mass, I can also take those moles of each substance and turn them into a mass. And again, the mass that goes in has to equal the mass that comes out, because mass is also conserved. Matter is conserved, the number of atoms are conserved, and if that mass of each atom is consistent, we can get that from the periodic table, then the mass of my reactants has to equal the mass of my products. I can look at those ratios again to determine my reactants versus my products. And lastly, if I have gases, that 22.4, I can take those moles, change them into volumes, and they all work out and are proportional to each other also. So if I have gases of reactants and gases of products, I can look at the volumes of those reactants and volumes of those products. So again, within a chemical reaction, the number of atoms and the mass are always going to be conserved. Whatever goes in for reactants has to equal the amount of products that are coming out in both situations, because we cannot create or destroy matter. Sometimes you get lucky and molecules and moles and volume might be conserved, but if they do, it's just, again, random luck. They don't have to be. It just might work out that way. So let's take a look at how these relate to each other, looking at this reaction here of the production of ammonia. So nitrogen plus hydrogen can get you ammonia NH3. So that first line, we'll look at the pictorial of this reaction, looking at the one nitrogen molecule N2 combining with the three hydrogen molecules H2, making these two molecules of ammonia. So second line down, we have looking at atoms. 2 atoms of nitrogen are going to combine with 6 atoms of hydrogen to then make these 2 molecules of ammonia, which is 1 nitrogen atom with 3 hydrogen atoms. So we're getting back out 2 atoms of nitrogen and 6 atoms of hydrogen, which is good because we know that those are conserved. It should be the same amount of nitrogen and hydrogen atoms on the reactant and the product side. The next line below that, now let's look at in terms of molecules. So I have 1 molecule of nitrogen, again combining those 3 molecules of hydrogen to make 2 molecules of ammonia. And those are coming right out of the coefficient of the balanced chemical equation. And again, because they are molecular, those nitrogen sharing electrons together, or the hydrogen sharing electrons together, or then nitrogen, hydrogen sharing electrons together, they are molecules. So we're looking at molecules, not formula units, not atoms in that case, looking at those coefficients. The next line below that is then just a simple ratio of, just like we talked about with baking, if I need to make a larger amount, looking at that recipe, I can do the same to each of those substances and they all work out together. So that 1 molecule now we're going to multiply by 10, so we have 10 molecules of nitrogen. The 3 by 10 again gets us 30 molecules of hydrogen, and the 2 multiplied by 10 is 20 molecules of ammonia. So those proportions remain the same. I just now have 10 times the amount of reactant and 10 times the amount of product coming out. And then the next line, we're doing the same exact thing, but instead of multiplying by 10, we're going to multiply by Avogadro's number, 6.02 times 10 to the 23rd. But again, that keeps that ratio exactly the same if I do it to every single one, which then gets us to the line below. Because now if I have 6.02 times 10 to the 23rd molecules of nitrogen, I have 1 mole of nitrogen. And if I have 18.06 times 10 to the 23rd molecules of hydrogen, then I have 3 moles of hydrogen. And if I have 12.04 times 10 to the 23rd molecules of ammonia, I have 2 moles of ammonia. So I can use those coefficients that are there up above in the balanced chemical equation, again, to look in terms of moles, looking at the much larger amount, the macroscopic amount of that reaction. Next line below that, well, if I know I have 1 mole of nitrogen, and nitrogen has a mass of 14, diatomic nitrogen therefore has a mass of 28, so 28 grams of nitrogen are going in. And then do the same thing with hydrogen. Hydrogen has a mass of 1, so H2, being diatomic, has a mass of 2, times 3 moles. there are 6 grams of hydrogen going in. So it's altogether there's 34 grams of reactant. Then go on the other side, nitrogen has a mass of 14, plus hydrogen, there's 3 of them, mass of 1 each, is a mass of 17, 2 moles of ammonia, so 17 times 2, 34 grams of product coming back out, 34 grams of ammonia being produced. So again, the mass is conserved from the reactant side to the product side. And then lastly, since each of these substances are gases, I can look in terms of volume, in terms of liters. Again, that 1 mole of nitrogen, therefore I have 22.4 liters of nitrogen if we're at STP. And 3 moles of hydrogen at 22.4 liters apiece at standard temperature and pressure, I have 67.2 liters of hydrogen also combining with that nitrogen. To then make ammonia, which also is a gas, 2 moles of ammonia at 22.4 liters for every mole, I have 44.8 liters of ammonia being produced. So their volume is not being conserved like the atoms and like the grams. So let's take a look at one more reaction here where it kind of mixes together a little bit of everything. We have this reaction of aluminum and potassium hydroxide and all these things coming together to make potassium aluminum sulfate or potassium alum. So let's look at the micro and macroscopic scales for this reaction, looking at the particle level and on the mole level. So first thing we're going to do is list out our reactants on the left and our products on the right and kind of just compare them as we go. So first we have 2Al, so aluminum being a element, we're looking in terms of atoms. So we have 2 atoms of aluminum reacting with now 2KOH. KOH, potassium hydroxide, is an ionic compound. So we're looking at formula units of potassium hydroxide, so 2 formula units of potassium hydroxide. Same thing with our H2SO4, we're looking at formula units of sulfuric acid, so 4 formula units of sulfuric acid. But then H2O is molecular, so I have 22 molecules of water being also reacted. And then to our product side, we have 2KAlSO42, so then that dot H2O, so that's actually what we call a hydrate because there's water actually trapped in there with our potassium aluminum sulfate. So I have 2 formula units of that potassium aluminum sulfate dodecahydrate, and also then 3 molecules of hydrogen, H2, diatomic hydrogen being produced. So there's our microscopic level. You're looking at the particle level and how the different amounts of representative particles of each substance going in and coming out. We can do the same thing with our macroscopic scale in terms of moles. So just using those coefficients, I can just slap moles on top of each of those coefficients to then look at this again on our macroscopic scale. So I have 2 moles of aluminum reacting with that 2 moles of potassium hydroxide to also react with 4 moles of sulfuric acid and 22 moles of water. And it's going to produce 2 moles of our potassium aluminum sulfate dodecahydrate and 3 moles of hydrogen gas.